thing you
No,
said
I
about
have
like
record. You
vectors.
know what? You can't count on this thing anymore. Okay, so the thing is, I have the paper, so you have the paper, you are listening. Hopefully you remember everything and I'm writing every details. But from the last class, which is just the Tuesday, Thursday classes, and I have had two hours classes, but still I haven't received the recorded videos. I don't know what's wrong. It says it's being processed. So it's being processed for 24 hours. For me, doesn't make sense. So
Okay, so I could help you with this. You want me to record a video? It's super easy, and I'll just dial it in, and it should be. Some apps are a little funky. Let me try. I'll see if I can capture it.
I think that should be a really good idea for now, because I haven't received from yesterday classes. So then we don't want to miss the video. Actually, if you are here, you're fine, but don't count on the video unless Brian is helping us right now. Kimberly, do you have the numbers? But again, if you don't have the numbers, it's just really solving the systems. Can you give the permission to record? I don't know how. I really don't know how. I think I have no idea. Sorry. I wish I knew. How should I give you permission? I don't know. I'm just checking my options over here. What I will find out anyway. Okay, Jimmy, I don't know right now, but I will find out. It should be probably in this setting that I have started in the campus account to change something. I just find out later. Okay, so anyway, if you don't have the number, I don't know, I think Kimberly lost the voice. So if you don't have the numbers, guys, when you write there, I have to just, okay, Johnny has some numbers. Why this chat doesn't move? Okay, so this is different than what we have started. Anyway, I'm going to just leave here because you have to solve this system of equations. You have to solve this system of equation, and that gives you the numbers. So again, because these numbers are different than what Kimberly gave me, we have to really start to make the system of equation, which means this 1 equals, and then 0 equals, and then 0 equals, and then you make the system of equation and fill out these columns. And then all I need to do to get the equations is really this multiplication, right? I got this one, right? So let me highlight it. So this is just the one that we're supposed to get right over here after doing the steps. And this one is here. And then this one is here, okay? So you just need to multiply and that's your answer. Is that fine? So it's the same process. So the main thing that the same process for some homeworks that you have tried, the main thing that you need to remember, this is just really good point to know. There are three-dimensional space, so I need to make two from the plane, which the transformation is exactly the same thing, because that's just really reflection transformation. And one of them is just in opposite, right? So it's just opposite because of is going normal to the plane, okay? And then when you make the beta prime, everything else should be really similar, because this is just really how you can write the matrix transformation from non-standard to standard, okay? Why? So maybe the good question is why I don't start from the exactly hey guys, why do you see it's recording? Do you see somewhere is showing this thing is recording? It's sure, right? Okay, it's recording. Yeah. Okay, I don't see. Oh, it's there. Okay, it's on the other device. It's the one that I use for camera. Okay. What I was trying to say, okay. So the only difference that this problem is we don't have the non-standard basis, and just we are trying to make this the non-standard basis. Okay, so maybe, as I said, okay, I didn't say, this is what I was going to say. So the main question for us is why we do not start to just really write directly what we are looking for, huh? What's the question? So this thing, the question is this thing. So can I write the transformation? I think geometrically by topology you can, but not really by the linear algebra. So why you cannot start right away to get the transformation of E1, E2, E3? Because I don't know, right? So I don't know where is the E1 with respect to this plane to get what is the transformation or reflection of the E1. I don't know where is the E2 to just get the transformation or reflection of E sub 2. So that's why I cannot start from the standard one. But the way that we set the beta prime to be one perpendicular and two of them to be right on the plane, so then you can just really use that theorem and then transform to the new basis. Okay, so your beta prime is what you have on your hand, beta or standard is what you are looking for. Make sense? So then you must do the same process for your what is it, quiz number 9, problem number 1. Any other question here? Any question here? Okay. So let's move on. You're welcome. So let's move on the lecture. So remember the last, we are still in 5.2. I believe I can't finish it again today. It's a long section. And but that's just really what you need to know for the test. Okay, so if you can finish 5.2 or diagonalizability, so this is the only thing that we have. And then the chapter 7 is going to be after the break. If you ask me why what's going on the campus, I know exactly what you know. I don't know more than you. Okay, so they requested no classes on the certain days, and I don't know why. If we are just really testing something, so we have already tested, so this is fine. Why no one say you don't have my camera? So but the thing is, the plan is not teaching during the days of 19 to 24. But if it is not teaching, they said we can record the videos and let them have the videos. I think being live for most of us is a lot easier because you can have your questions. So either way, I will be available on the class time on Monday. Okay, and then we do not have anything due on these days. Am I right? So this, what is it? Give me what's the date. Okay, so if it's 24th, I can make it 25th. Okay. If you have anything on 24th, I can make it 25th. Okay. But that's actually my next thing to say. Okay, so so maybe I mess up with the dates. If I just have, yeah, your midterm is 25th. Okay, okay. Okay, so let's do the 23rd. Let's do the 23rd to be just question answers or something like that, and then 25th I will post the problems of the take-home test. Okay, so you will get this information, right? So just to make the 23rd without the due dates, that's just really the purpose, right? So if the 23rd is, it can't be the, just any, but we can have the videos, we can have the recorded. I mean, so based on what they provide for us, I can teach. But if I teach it by video and record it and send it to you is one way. But just for the, what was it? For these due dates, I will just push back everything to the 25th instead of the 23rd. Okay. And then that in-class test now will be on Wednesday, basically. Sorry, not in class. The take-home test will be on Wednesday, okay? So then you will get an email, what's the due dates, and I will just adjust the due dates when we are done with this class, okay? Is that clear? Do you have any question? Do you have any question?
Professor?
Hmm.
So for the take-home part, are we going to do that in class, or are you going to be giving us like the 2 days that you gave us last time to?
Yeah. So that one is still is the same way. That one is still is the same way. So the take-home test, I'll just provide some problems. It's just usually 5 problems, and then you do it as you did it last time. So it's just a few hours available for you. So it's just about 48 hours. It's not completely 48 hours. So it's about 48 hours available on Titanium. You can just do it however you want. You don't have to print it out. And the details is just very similar, except the due dates. Everything is going to be similar. The only thing is now we just don't have the 23rd to make it the due date, so we will make it 25th.
Okay, thank you.
Mm-hmm. Any other question? Okay, so what we are trying to do still is diagonalizability. So that's just for the transformation. And for this type of the topics, the only thing that we need to know is eigenvalues and eigenvectors, and how many do we have? Do we have enough or we don't? So the last thing that we did, and we stopped right there, it was just really how we can test whether something is diagonalizable or not. So then the actually was the other way, because we just say if you want, if your transformation fail, if I change the different color. So if your transformation failed to be just diagonalizable, so that means you don't have enough eigenvalues. Okay, so in this case means either you have repeated one, or even you haven't had from the beginning enough eigenvalues. Okay, so when we have a repeated one, we need to make sure corresponding by each one we can get enough eigenvectors to have in many of those. And then when we have such a this case, which was just really no eigenvalues or no real eigenvalues, then we haven't had enough to begin with. So that's just really 2 cases that we say the the diagonalizability is going to fail somehow, or I can just build the other type of eigenvalues to solve the problem. And that's just really what we want to just say. Is there any way, or is there any theorem or not for today? The main thing that I need to remember, in order to have just enough lambdas, I have to have this polynomials completely factor out. Okay, so if the polynomials completely factor out, so then that's just really enough eigenvalues, and then I can get corresponding by eigenvalues, eigenvectors, and then I'm done. Okay, so this is just really, if you have 2 by 2, you need 2 eigenvalues. Why? Because you could factor it in 2 linear factors. Or if you have 3 by 3, so you got 3 eigenvalues. Why? Because you could factor the polynomial to 3 linear factors. So then from each one you got one of them. Okay, and that's just a quick recap from last time. So the goal was just try to find if it's possible a basis that's just the matrix is diagonal matrix. And then that means, I mean, the definition of T to be diagonalizable is just find the basis. And then that is the same as saying the basis of whatever is your vector space is going to be your eigenvectors. Okay, so these are all equal or agree with. Is not really like just theorem if and only if, but it's just really they are like a definition. So T to be diagonalizable is the same as finding the bases, which are all eigenvectors. Okay, and then concepts, just to say whatever we have learned in matrix form, so that's just really agree with whatever we have learned here in linear transformation. So if I'm looking for eigenvectors for my T, so this is same as looking for eigenvectors for corresponding matrix. If I'm looking for eigenvalues for the transformation, is the same as eigenvalues for my matrix of the transformation. And then if you are having different what is it, basis, so like just gamma and gamma prime, so these eigenvalues is going to be stay exactly the same thing. Why? Because they are similar matrices. Okay, so if I change my basis from gamma to gamma prime, still I have the same eigenvalues. And that's just why, because the determinant of T minus lambda I, we proved with one theorem, when similar matrices of A and B is going to be the same. So then if I replace this T by the corresponding matrix transformation, and then just change the basis one more time, that determinant stays exactly the same thing. So if it's gamma or gamma prime of any other basis, polynomials are the same, eigenvalues are the same. So then we are fine. We are not worried about changing eigenvalues or eigenvectors. Okay, so this is what we have had last time. The theorem that we're supposed to do says what we said. If you have a T and you wish to be diagonalizable, so your characteristic polynomial splits, so you can factor it out. So this is a necessary condition. So if your polynomial splits or your polynomial completely factor out, so this means the T is diagonalizable. This is very just really easy one, because if you have a diagonalizable, means you have your matrix is a diagonal matrix. So then if you want to make the determinant is just really determinant of A minus lambda, determinant of the matrix, which just your main diagonal is A minus lambda, B minus lambda, Z minus lambda. So that's just really multiplication of this main diagonal minus lambda. And that's just really what we said. If something is diagonalizable, so then polynomial just splits or just factor out completely. Okay, any question? Any question? Yes, please. Should I read your comment? Or you can talk, Johnny? If you can't, because if I maximize the page, I don't see your comment. Okay. Okay. Waiting for a question. For the non-diagonal entry, does it all have to be 0? So remember the condition, yes, because what the condition says this transformation is diagonalizable. So this transformation is diagonalizable means your matrix transformation is a diagonal matrix. So yes, everything else is 0 because that was the assumption. Okay, anything else? If I maximize this one on this page, I don't see your comment, but for the other one, which I'm just showing my video, I see somebody sending something. So then I have to go back and see your comments. Okay, but that's fine if you don't have mic. But mic helps you when you just listening in future, hopefully, if you can record it. Okay, so something about just really what is your field or what your scalar is coming from. So this is just going to be just some remark to remind us, maybe you have something to be diagonalizable on C, which is complex numbers, but not diagonalizable on R, which is your real numbers. And that makes sense, okay? So if I go back to this example that we just tried it last time, so this is the one that we tried last time, and it wasn't diagonalizable on R because this does not have any solution in R. But if I make it in complex, I can just solve it. It just, sometimes when I go too fast up there, it's just stuck. Hopefully nothing happened, and I have to close it. So then I am hoping you remember what I'm talking about. And I don't think it's here. No, it's not here. It's in previous class. Okay, so the remarks over here is just reminding us the field that you have selected is important. And one thing that we knew from the algebra, if you have polynomial of degree n, you will get n solutions, but that's just for complex, right? So if you have a complex field, so you will get always n solution. So it's really same thing over here. If the field was the complex numbers, so for any polynomial of degree n, there is no issue. You will get always n factors or n solutions, okay? And then, as I said, you might have something to be diagonalizable somewhere in one field, but not in the other field. And that's just really one example for that rotation matrix, which wasn't diagonalizable because it was just through the R, but it's diagonalizable. Let's change it to the C, and same thing for this matrix. So if I was, is not diagonalizable if I just have the real numbers, but it does have a complex solution. So for complex solution, you get two conjugates numbers. So then you can just say either one gives you one eigenvector, and that's just diagonalizable, okay? So that just depends on the problem. Can I say if I just change my scalars to be all complex numbers, I have always diagonalizable? No, that's not true. So because of repeated one, you might just get the what is it, not enough eigenvectors, right? So that's not the point. Okay, there were two questions or 2 points right there.
I had a quick question.
Go.
So it's the case that, like, if you have repeated eigenvalues, then you may not have enough eigenvectors in there, even if it's complex. Okay,
it is 2 by 2 is fine. Okay, for 2 by 2, you remember if you have 2 by 2, so you have a complex number. So the example that I have right over here is 2 by 2, so that's fine. Yeah, but if it is more, yes, you might just get something, even though if you just consider your complex numbers to be your eigenvalues, still the repeated one might not get enough eigenvectors.
Okay, so I'll look it over again.
Any question? Okay, so let's just say, what was the problems that we said about you fail to have the diagonalizable transformation? Number one was just if you have a repeated eigenvalues, right? So this is the case that you have repeated eigenvalues, and then you might fail to get your diagonalizable transformation. And that's just really one definition. We've seen it before. It's just really what we call multiplicity of eigenvalues. So if you have an eigenvalue, and then the number of time that your lambda is a solution to the characteristic polynomial is called algebraic multiplicity. I think we knew all this, right? So this is from the previous course. So if your polynomial has like just really lambda minus 1 to the second equals 0, lambda equals 1 with the multiplicity of 2. So this is just what we knew from the previous course. So this is just an example which I needed in future, especially for chapter 10. So this is just some matrix which has 8 rows, 8 columns. And then as we see, there are some repeated, eigenvalues, right? So I have listed over here, I said for the zero is not repeated, and it's just really one time, multiplicity is 1. For the 2, the 2 is 1, 2, 3, 4, 5 times, okay? And then for the, something happened, okay? And then for the 6 is just repeated 2 times. So for the 6 has the multiplicity of the 2, okay? And this is a good example to say, okay, how do we have, by this many eigenvalues, how do we have the diagonalizable matrix and then diagonalizable linear transformation, okay? So the main thing, if we remember, is if you have 2 multiplicity of 2, so let's say lambda equals 6 has the multiplicity of 2, huh? So we hope to produce exactly 2 linearly independent eigenvectors, okay? This is the hope, right? So that's just a typo. This is going to be 2, right? And then if you have the eigenvalue equals 2, the hope is to get 5 free variables, 5 linearly independent eigenvectors. Okay, so if your lambda equals 0, the hope is just you get the 1 because the multiplicity of the 1. Okay, so that's just the term that we use it in previous course, and it's really here. We hope it pulls its weight. So if it's repeated, we hope it pulls the weight. So means for the 2 is just 5 times, and then for the 6 is 2 times. So this case, then you will have enough, huh? Because it's 8 by 8. Since it's 8 by 8, you will get 8 linearly independence, and that's just the hope. Okay, so does it make sense? Brian, now I have just really good example to say why the repeated one is the problem. Any question? Okay, and then if your eigenvalue fails to pull whatever is the weight, then we don't get enough eigenvector. Huh? So we do not have enough eigenvector, and then the question is, can I use another eigenvalue to just make this situation? So is there any way to make another value to make just this situation? So for example, let's say for lambda equals 2, I got really just 4 of them, huh? So for lambda equals 2, I got 4, not 5. I supposed to get 5, but I got 4. And then here, can I get 3 instead of 2? Then I just build up? No. The answer is no. That's not possible. Okay. So when we have the multiplicity, so this is why it doesn't erase only this part. Okay, so when we have the multiplicity, means the maximum number of eigenvalues that you can get, right? So sorry, the maximum eigenvectors that you can get, and that's a theorem. So the answer was no, and then because of this theorem. So if you have eigenvalues, when you have how get I? Okay, so if you have the eigenvalues with the multiplicity of the m. So that's just maximum number of eigenvectors that you can set. So whatever eigenvectors that you can set has to be, you can get, has to be less than equals that many. Huh? So what does it mean? For lambda equals 2, for this example, for lambda equals 2, I can get maximum 5 of them. I can get less, then it's not diagonalizable anymore, but there is no way to get more than 5 from this one. If you have lambda equals 6, the maximum number of linear independency vectors I can get from 6 is just really 2. And that's what it says here. Okay, and then whatever is stated over here as a theorem is really informal way of writing the main theorem in the book. And for now, we just don't worry about the proof. We don't prove this theorem. Later, if I have had time, I will prove. For now, I don't prove this one. So skip the proof. And then that's just really that m thing, or the multiplicity thing. Remind us what we have had some other terminologies, right? So it was eigenspace, dimension of eigenspace, or eigenspace was the other terminology that we have had in previous course. So this is just to remind you, for the transformation, the terminology works exactly the same way that you've seen it in your previous course. So the transformation is defined to be from V to V, and then you are just finding your eigenvalues, and then corresponding by that eigenvalues, eigenspace is just a set of all your vectors, which is the set of your eigenvectors. Okay, so it means T times V is just stretching lambda times, and then that's just really definition of being eigenvectors. Okay, so the set of all eigenvectors corresponding with each eigenvalue is called eigenspace. Okay, so your eigenspaces, the way that we've found is just really the same thing, but we remember that's a subspace. We don't have any problem. The eigenspace is a subspace. Why? Because eigenspace is a null space. Null space is always a subspace, right? So this is just really definition of your eigenspace, and that's just corresponding to what we call null space of T minus lambda I. And then null space is always subspace, so eigenspace is a subspace. So same terminologies, we have had exactly the same process in matrices. Now is just repeating with the transformation. Okay. And then if this is the language, means eigenspace is the language. So this is reminding us the terminologies of the theorem. What is 5.7 says dimension of eigenspace is the same as number of linear independent eigenvector that you can get from each eigenvalue, right? So what's the dimension of eigenspace? How many eigenvector I can get from that eigenvalue. So that's the dimension of eigenspace. Any question by here? Any question by here? Any question? Move on. Move on. Okay. So theorem 5.7, I can rephrase it by saying if lambda has multiplicity of m, this is the same as saying the dimension of eigenspace is between 1 to m. Okay, so dimension of eigenspace is between 1 to m. So I'm looking one more time to this theorem. Says if lambda has eigenvalue, if the lambda has the multiplicity of the m, so number of linear independence eigenvectors I can get has to be less than m. Number of linear independent eigenvectors is the same as dimension of eigenspace. So that's why we can rephrase it over here. Dimension of eigenspace has to be better. And do you agree we get at least one? Do you agree it's less than equal as m, but it's not 0, never ever, right? So we will get always 1. Yes? So look at to the matrix, right? So these are really number of free variables I can get. So if you have just, for example, 3 by 3, so you can't have in row echelon form everything to be 0, right? So at least one of these thing has to be pivoted, right? So there is no way to start to row echelon matrix and make all of them to be 0. So the number of free variables is the same as the number of vectors that you can get corresponding by each of these eigenvalues, okay? So there's no way to have all of them 0, so at least I have one of them, okay? I might have more, but the 1 is the minimum value that you can get. Okay. The test for diagonalization transformation, okay? So this is the test for diagonalization transformation. So that's just, again, informally, and that's just enough for us. What it says, if you have a characteristic polynomial and then you know it's completely factored out, so it's diagonalizable, all right? If your transformation is diagonalizable, the characteristic polynomial can completely factor out. And if your characteristic polynomial has just really n many linear factors, so then you have just n many eigenvalues corresponding by each one, you will get one eigenvector, so then you're fine, okay? So that's number one. So just start to write your characteristic polynomial and factor it out. So if it's factoring completely, that's diagonalizable. This is test number one. And then for the test number two is you try to make the eigenvalues and then try to see what's the dimension of eigenspace. Is really the same as multiplicity? So yes, it's diagonalizable, okay? So this is the same as when you say your eigenvalues pulls its weight. So means if you have, in this example, if you have lambda equals 2, if you have lambda equals 2 has the multiplicity of the 5, so then the dimension of your eigenspace corresponding by that has to be 5, okay? So this is a test. So if this hope is all correct, then the matrix is diagonalizable. So that's just the second way of testing whether something is diagonalizable. Any question? Any question? I don't see the chat. There was. Okay. No question, huh? So just to practice, we have a nice example of number 17 of the 5.1. Did we have this problem in the any of the assignment? I don't remember. Is it number 17 in the assignment?
It's on a 5.1 assignment, the last assignment for the homeworks for this week.
Mm-hmm. Anyone tried it?
I tried it.
Mm-hmm. Okay. So your transformation, it says transform every matrix to the transpose. So transformation of your matrix is the transpose of that matrix, okay? It says show that plus minus are the only eigenvalues. How?
Oh, how I did it?
Mm-hmm.
Oh, so I just let lambda be an arbitrary eigenvalue in for this transformation, and then I just basically show that lambda must be plus or minus 1.
How?
That's
so then if you have the determinant of what is it? transformation minus lambda I to be 0. Okay. Then?
Oh, I didn't do it that way.
Okay. Just let me know how you did it. Can you write it on my, do you have some pen, pencil? Or
I
you don't have? Okay.
I can try. Actually, no, I can't. Actually, wait.
Mm-hmm.
I can't. I'm sorry.
Mm-hmm.
So I think what I did was T of A must equal lambda A. That's what I wrote first.
Mm-hmm.
Right?
Mm-hmm.
Then that means A transpose
Mm-hmm.
is equal to lambda A.
Mm-hmm.
Then what I did next was I transposed both sides.
Mm-hmm.
Right? Then I got A is equal to lambda A transpose.
Mm-hmm.
So what I did next was basically the A transpose equals lambda A. I substituted that into the new equation that we got.
So A transpose is lambda A.
Yeah, I put that into because you know that that lambda A, like all that transpose is just lambda times A transpose, right? Then I substitute the A transpose lambda A inside, right?
Okay.
Then you get A equals lambda squared A. Then I moved it lambda squared A to the other side. Then I get that because A is an eigenvector, so it can't be non-zero. So 1 minus lambda squared must be 0. Then I get plus or minus 1.
Okay. This is one way to do, and the other way is just really saying exactly, it's very similar to this one, is just saying, okay, so if you have, that's correct. So if you have a transpose and then transpose equals just the same thing, right? So this is just basically means you have T of A equals same thing. So this is basically the same as T squared equals I. Okay. So then this is really same as if you have T squared equals I. So this is the same as saying lambda squared equals 1. Then lambda is plus minus 1. Okay. That's really basically the same thing. Okay. Does it make sense? And then describe the eigenvalues corresponding by each of these eigenvalues. So this is just the B. Eigenvectors, sorry. Find the eigenvectors corresponding by each one. So this you have to have the transformation of A, lambda times of A. So for lambda equals 1 is transformation of A equals 1. And then for lambda equals -1, transformation of A equals negative of A. So this is really same as transformation of A. So is A transpose equals A. And this is the same as transformation of A, which is A transpose equals negative A. So this is what we call, what is it, symmetric, right? Matrices. And then this is the same as what we call skew symmetric matrices. Okay, so basically what is the description of what we call eigenvector for lambda equals 1? So it's just the set of all symmetric matrices. And what is the eigenvectors corresponding lambda equals -1 is the set of all skew symmetric matrices. Is that fine? Question? Any question? And I just write number C, but the D is going to be exactly the same way. and is one of the other homework that we have had someday in 1.6. So this was in 1.6 homework. Okay. So what would be the order of bases for a 2x2 matrices that this transformation is diagonal matrix? Any idea? For 2x2?
So would it be, so the basis would be, it's the basis of the symmetric matrices with union the skew symmetric matrices?
Okay, so exactly the basis for the symmetric matrices 2x2, huh? Symmetric 2x2, so it's going to be like A, B, B, C. Am I right? Is that true?
Yeah.
So then that gives me 1 for A, everything else is 0. 1 for B, everything is 0. 1 for C, everything is 0. So this is for symmetric matrices, right? And then I think I need more for the.
Sorry, would the second matrix be 0, 1, 1, 0?
1, 1, yeah. Thank you. Thank you. So then for skew symmetric matrices, 2x2, so the form is 0, 0, B, negative B, huh? Is that true? So yes, I just need one more, which is 0, 1, negative, negative 1, 0. Okay, and then you can extend this one to the n by n, right? Make sense? Any question? Any question? So something that we need to remember from the what is it, operations that we have done for Roche-Ellen form. So to just remember, whatever row operators or Gaussian elimination method does to just get the solution might change your diagonalizability, huh? So that's just an example to say if you have this is just really diagonalizable matrix because it's really diagonal, and then if you do some operators, so you just make this one, what is it, adding the second row to the first row, right? Or just twice of the first row, okay? As you see, your diagonalizable is changing, right? So this is just originally diagonalizable and then at the end is not, okay? So that type of thing, just remember when you have a row operators, it doesn't guarantee it keeps all the way to the end your diagonalizability, because that's just really for the repeated eigenvalues, huh? So one more time, for this time lambda equals 1 with a multiplicity of 2, so that's just not diagonalizable. Okay, and for this time lambda equals 2 and lambda equals 1, so I get exactly 2 linearly independent eigenvectors corresponding by each of these, and that is a diagonalizable. Okay, so that's just the difference. Okay, one more thing I forgot to just tell you at the beginning. I don't know how much time do I have. Wow, no way. Okay. So did you check this lecture note? The way that it's just right now was on the file on top of the page. So let's just go to the titanium before I forgot about it. I'm pretty sure you got an email, but I just want to make sure. Mm. Three or seven, yeah, it's just right here. Huh? For now, whatever you see, as you ask me to put the lecture note before the class time up there, then you have it. So without my explanation, I put it last night. And that's just really what's happening. You will get it in very last minute in the last night, because we are new for this type of thing. So if you want to have the lectures, they are there, okay? But you see without the solutions, because I posted last night and we are filling right now, okay? So how do you go back to the same place? So I was here, huh? Yeah. Any question? The second fact is, if you have n many exactly, huh? So means you have started from so you have started from n times n, and you got exactly n many eigenvalues. So then the determinant is going to be product of the eigenvalues, and the trace is going to be addition of the eigenvalues. That's fine, right? And I just explain over here what's the reason. Because when you have n many eigenvalues, means your polynomial is just splitting out to the n factors, n linear factors, okay? So if you set the lambda to be 0, this means just really you have determinant of lambda is 0, so you don't have here any value. And then you have determinant of a, and here lambda is 0, here lambda is 0, here lambda is 0, so then you have the product of the lambdas, okay? So that's just why if you have exactly n many eigenvalues, you don't have to worry about the determinants, because determinant is just really product of the main diagonal, basically, or lambdas, okay? This is a really shortcut if I know it's diagonalizable. So imagine your matrix is 10 by 10, and then somehow it's repeated, maybe it's not repeated, but it is diagonalizable. And then it's just really tough to get determinant for any of other method that we have learned. But if it's just really multiplying the diagonals, or sorry, multiplying the eigenvalues, gives you really the determinant. This is really a nice one, okay? If we know it's diagonalizable. I'm going to pause for a few minutes, okay? So this is, I think we need to get maybe about 1 minute pause. If you have any question, you can ask me. But since we are doing right here, I always forget about to stop somewhere in 15 minutes. So let's just do something. Okay, I'm going to stand on my feet. But if you have any question, you can ask me. You know, yesterday I have had 2 classes, and then I had to be prepared for this today. I was sitting on the chair for 17 hours just to be prepared for the Wednesday, and it's just a lot of work. It is a lot of work. I was just really standing on my feet for entire class time. Now it's just all sitting on the chair. Anyone, any question? Move on. I have two examples of the applications over here. If you have had 250B here in this campus or 207 in this campus, you probably have seen this problem in the book. And then just really the same thing and remind you that's the application. And even the second one, okay, these two application problems are not really in the level of linear algebra of 307, is really in the level of the previous course. Okay, this is just to remind you, you have done these problems and then just some extra problems. Okay, so I don't know how much time I have to finish this one, but we can just really start it, and then the calculation I can copy from the notes, then we don't have to waste the time. Okay, so what it is, you have just the applications of diagonalizable. The main application, as we said, is computational simplification. So if you need to somehow rise your matrix to the power of 100, power of 1000, or power of infinity, because your job is repeated many times, okay, so then we have many cases in the real world that something is repeated, right? So some process, some job, something for the system is repeated many times, which means your t is approaching to the infinity. Okay, so that in matrices means you multiply your matrix n many times, or you compose your function n many times. Okay, so that's number one, to use the diagonalizable. Number two, we have one method of solving system of differential equation by using diagonalizable. I think that's not a good idea, because we have learned later, after this method, we have learned in the previous course how to do the system of equations easier. Okay, but that's just really one way of doing the solving the system of differential equation. Okay, and again, this is one problem that if you have had the previous course here on this campus, or it's just really same book, you've seen it before, right? Anyone has any idea? Each day 10% of the professor A's students switching to the professor B's class. If you have each day 20% of professor B's switching to the professor A's, so how many percent of the students will stay in each class at the end of the day, or at the end of the semester, or for a long time, so when t is approaching to infinity? So then I have to write the matrix corresponding by these changes, right? So if you are staying in time, for example, today, and then the 10% is just moving, the 10% is moving from A to B. Okay, so if I can just really somehow say this is going to be Professor A's, this is going to be Professor B's. So can you say what's the matrix? Okay, so I will say x at t plus 1 is, okay, any idea how do I fill out my columns for 10% of the Professor A's, 10% of the Professor A's, 10% of the Professor A's switch to the Professor B's. So you have had 90% of X, and then is it true? So you have 90%, so 10% is switching, 10% is switching from A to B. So 10% is switching A to B, so 90% left for the X, right? And then 20% of the Professor B's, 20% of the Professor B's is switching to the Professor A's. So now this is how much is in the class of Professor A's. So this is Professor A's, right? In the next day, he's losing the 10%. he's losing the 10%, so 90% left for him from the same class, and then he's getting the 20% of the students from the professor B. Okay, so then since it add up to the 100, so if it is 90, so this is 8%, huh? So this is going to be for Professor A, this is going to be for Professor B, and seems for Professor B, he's getting 10% of Professor A, which is X, and he is having 80% of his, which is Y. Is that fine? Is there any question? Is there any question for this one? Anyone has any question? Mm-hmm. Yes. Mm. Oh, sorry, I did just, I'm reading your previous, yeah. No question? No question, okay. So if you are fine with this one, the whole goal, as you will see here, is just how do I rise this matrix K when K is approaching to the infinity, huh? How do I rise it to the power of K when K is approaching to infinity? Because this process is repeating every single day. And that's just the same as composing K many times. That's the same as rising K many times, and that's the same as just leaving K to be infinity, okay? And then the process is really diagonalizable. Why? Because if I just want to rise this one K many times or infinite many times, it's really tough. But if you remember, we just explained, if you have A to the K, but that's just really Q inverse diagonal matrix Q, what is it? D is the matrix that your lambdas are sitting there. And then when you multiply K times, it's just really K times of your main diagonal, and Q inverse is just really the same matrix that we have had for identity matrix, okay? And then, but this is just really the previous course. Basically, Q was in previous course the eigenvectors. So we just plug in eigenvectors. So I just follow the process that we have had in previous course. So determinant of this minus lambda is going to be this times this minus 0 to, and then we rise it to whatever it is, 72 minus lambda minus 0.8 lambda plus lambda square minus 0.2. And then if I simplify, I have lambda square, I have minus 1.7 lambda, and then I have 0.7 equals 0. And then the factors is lambda minus 1, lambda minus 0.7 equals 0. And that gives you your lambdas. Okay, so if you have lambda equals 0.7, the nullity of 0.9 minus 0.7, 0.8 minus 0.7, and these are 0.2. This is 0.2 and this is 0.1, and then you can just find the corresponding eigenvectors after solving this, which I just copy from my note. Is for this one is 1, -1. I think it's easy because it's just really same columns. It's just one negative one. And then for lambda equals 1, the nullity of 0.9, 0.8, 0.2, 0.1, and then subtract it from 1, subtract it from 1, and then this is, I got 2 and 1. Okay, you can just check my work. And this is just Q, which the main, what is eigenvectors is sitting here, or any scalar multiplication of that one. And then if I Q inverse it is 1 over determinant of adjoint matrix, huh? So this is 1 over determinant is 3, so it's 1 over 3, 1 over 3, 1 over 3 minus 2 over 3. So one more time, I have switched these two, and then I multiply by negative. Okay, so determinant of the Q is negative 2 minus 1 is negative 3. Okay, that makes sense. So this is the Q inverse, and then what the goal is just right there, huh? So this is the goal. I'm going to change this one to the M, okay, because that was the name of mine. So this this means if you have M to the power of K, you have Q inverse, diagonal matrix, and then to the power of K, and then Q, which the Q inverse was 1/3, 1/3, 1/3, negative 2/3, and then you have diagonal of, if I keep the order, so first one is just for lambda equals 1, so this is lambda equals 1, and then the second one is for lambda equals 0.7. Okay, so this is 1, this is 0.7, and then if I raise it to the power of K, this means to the power of K, this means to the power of K. Okay, and then the Q, which was 2, 1, 1, negative 1, and then this is nice. Why? Because I know what's happening over here, right? I know if I rise, if I K approaching to infinity, huh? So I know if I rise, this is going to be exactly the same. Do we know when we have 0.7 rise it to infinity, what happened after infinity many times?
Go to 0.
So that's it. I'm done, right? Because that's just really multiplying these three matrices, and I have had the result. The result is 2/3, 2/3, 1/3, and then 1/3. Okay. So in the long term, if you have x of t, it seems 2/3 of all students is for all of the students is for Professor A, and then 1/3 left for Professor B. That's just one application problem. Is it fine? Okay. The process of this theorem, actually the other part of the other, is there any question for this one? Sorry, before moving. Is there any question for this one? No?
I have a question.
Please.
For your matrix Q, or the one, yeah, why is it 2, 1, 1, negative 1? Maybe not like 1, 2, 1, negative 1.
This one?
No.
This one. Yeah. So
Yes.
it's just really because this one is 2, 1, so this one is 2, 1. No?
Okay.
Right?
Oh, okay. Oh, okay.
So this one is this one.
I have one question as
Please.
well.
Please.
How did you get the eigenvectors?
as we
When
did
you
for determinant of A minus lambda I.
oh,
Right?
when you get lambda equals 0.7 and then you plugged it into the matrix, how'd you get that eigenvector 1, -1, and 2, 1?
Oh, again, okay, so I skip the steps. So this is just really skipping the steps, but it's just really having, you see, when you have the result of over here is 0.2. So when you have a result of here is 0.1, right? Is that fine? So
Yep.
basically your matrix is simplified. Basically your matrix is simplified with the 0.2, 0.2, 0.1, 0.1, which just means just canceling out and keep everything really, what is it? If this is X and this is Y, when you said X plus Y equals 0, it doesn't matter which factor is because you can divide by that, right? So then X equals negative Y. So that says always one of them is negative times of the other one.
Oh, okay, makes sense.
I
Thank you.
solved it, right? Any other question? Do I have any other question? Okay. I'm going to leave this example for yourself. Why? Because this is what we have done in previous course, right? So I have explained, if you don't remember the idea from the previous course, so this is just really writing this system of equation. Again, in later on in the same course, we have learned easier way. This is not the easy one, okay? But the idea is coming from diagonalizable. It was at the end of chapter 5 of the previous course. And that's just really the matrix corresponding by that system of equation. And then using the process of A is diagonalizable can be replaced by the diagonal matrix like this. And then you have the new matrix of the W, or the new thing that you need to solve, which is the W. And then you just follow the process, and instead of finding the V's, first you find the W's and you get the V's. Okay, so again, I'm going to leave this process exactly for yourself, and we can complete it later. But I have nice examples here. Pretty much I can just say for the lecturing I'm done. It's just really some extra problems to practice. Okay, I don't have anything to the lecture except just really some problems that we tried it today, or you tried it in your homework. Okay, so one example that we did today was problem number 17, section 5.1, which is repeated one more time in 5.2. So it says, if you have a transformation of 2 by 2 to transformation of 2 by 2 is defined to be just transpose of the matrix, then it says test diagonalizability and write the beta, which is this matrix diagonal, right? So that's just one problem that you must do it in your homework, and actually you have done it once, okay? So how do we test diagonalizability? So if you go back to the problem that we did today, let me go slowly. So we have done that thing right over here, and we got lambda is, where is it? I lost it, huh? It's here. Okay, so test for diagonalizability, either I check the number of eigenvalues to be exactly n many, or I will check the corresponding vectors to be enough, right? So dimension of eigenspace to be enough. Okay, so since we got two eigenvalues over here, so we got two eigenvalues over here, which was what plus minus 1, and corresponding by just each one you get symmetric and skew symmetric matrices, and then you got the basis corresponding by this one. So basically we have answered this question once. It is diagonalizable, yes. What's corresponding beta that make it diagonal? That is skew symmetric and symmetric what is basis. Is that okay? Did you follow? Any question? Is there any question? So then another true false problem, it says if you have two matrices, each one is diagonalizable, can I say the product is diagonalizable? So if A is diagonalizable, B is diagonalizable, is the product diagonalizable? No idea. And the wrong proof, which is very common for the students when I give this one to the test, is you just say, okay, if the first one is diagonalizable, can be written in this form, and the second one is diagonalizable, so can be written in this form, and then we multiply both sides, so that gives me Q inverse A times B, Q equals D square, which D square still is just another diagonalizable, and that's just, I'm done. Okay, so you can just do some other steps. So this is a wrong proof, first of all, because the diagonal matrix that you get from these two are not the same, and then just the order that you change all the way for the product of the matrices is nonsense, and actually this answer is false. So it's just really wrong proof that I've seen many times in the test. So I can just really bring counter example. I have 1 1 0 0, and then I have had 0 0 0 1. Okay, so this is two diagonal matrix. This is two diagonal matrix. Why these two are diagonal matrix? Because it has lambda equals 1 and it has lambda equals 0. Two eigenvalues, two eigenvectors is diagonal. Lambda equals 0, lambda equals 1. So these two are diagonal matrix. So this is diagonalizable matrix, and the product of that is just 0 1 0 0. That's not diagonalizable. Why? Because it does have repeated lambda. Since it does have repeated lambda, it's not diagonalizable. Okay, so these two are diagonalizable, but the product is not. Okay, so that result is not true. Okay, any question? And the thing, I have it over here, is just really one of your homework again. Number 3 is one of your homework again. So it gives you something that you're supposed to show that's isomorphism. Oops, see, isomorphism. So however you know to show is isomorphism, so you can just show is onto and one-to-one, or you can just make the matrix transformation, or you can make the matrix transformation and say that that is non-zero, or however else you know to show the something is non-invertible, sorry, is isomorphism, you can show that's isomorphism. Okay, so again, this is one of the homework. I'm done for today. Oops, we passed 4 minutes. Okay, I'm done for today. If you don't have any question, first of all, I'm going to stop the recording, because when it gets longer, it's harder to get the video. But if you have any question, you can ask me. How do I stop recording?